So let us move to the simplicial category, or the category of simplicial rings. So we have so far defined everything that we defined over the, algebraic stacks and algebraic schemes and so on, over the category of commutative rings. Now we extend the base of this category too. So now our base also involves simplicial rings rather than just naive simplicial rings, which are just commutative rings. Commutative rings could be simplicial rings, but they are constant in the simplicial category. So let's talk about simplicial commutative algebras. This is what we want to do today. Now, so let S commutative be the category of simplicial objects in the category we used before, the category of commutative rings. So these are objects which have resolutions like, they have representations like exactly like what we had before. So locally they look like, it keeps going like this, and so and these degeneracy maps and so on. So your rings now are like this. So they are regarded as graded rings with graded pieces put together with relations between the pieces, and those are the simplicial relations. And so this is the category of simplicial algebras. So for some A in this category, let SA mod denote the category of simplicial A modules. So same way that over commutative rings you can have modules, over simplicial commutative rings also you can have modules. So what do they look like? An object in simplicial A mod is the data of simplicial abelian groups, similar to modules which are abelian groups, but they are, this time they will be simplicial abelian groups like that, and such that the morphisms Mn to Mn, for instance, are morphisms of An modules, morphisms of An modules for the An module structure. For the An module structure on MM induced by An module structure on this morphism. Okay, so you have the An modules like that, and the An module structure of the morphisms given by the An, because the An also has morphisms in between them, and the morphisms between An and Am are basically compositions. Okay. So this is what it means, a simplicial module. So it's a simplicial set of abelian groups that level-wise are An modules, and then they also respect the simplicial morphisms between them. Okay, so this is what a module is, and we say that a morphism in this category of simplicial rings is an equivalence or, you know, vibration if the induced morphism on the underlying simplicial sets is an equivalence. Is an equivalence. This is equivalent to saying that this will define a model category structure on this category of this category of simplicial primitive rings and the simplicial modules over a simplicial primitive algebra. Okay. So for those who came a bit later, we are now extending, we are further moving to the category of simplicial primitive rings. Our rings are simplicial, and so a graded ring, imagine, and you have the relations in the sense that the relations between each level are simplicial relations, and we are defining modules over that category. So you have the category of simplicial primitive rings, and the modules are again set of abelian groups, which are level-wise modules over the pieces of the ring, and the morphism between the pieces in a given simplicial module respect a modular structure, which is given by the morphism between the pieces of the simplicial ring. And we have a notion of an equivalence in the simplicial primitive category, and two things are equivalent to each other, whether they are modules or rings, if the underlying simplicial sets are equivalent to each other. So this extends the modular structure lifts the modular structure that exists on the simplicial sets, the category of simplicial sets, to the simplicial primitive category, and the modules on it. So fibrations, co-fibrations, everything is being lifted up. So that's that. So now let A be a simplicial ring. Then I can define the homotopy algebra of this ring. The homotopy algebra of the ring, by definition, is the sum of all homotopy groups of the simplicial ring. Okay? Here, we do not specify. If you remember, when I had some simplicial set or simplicial object over a category, we defined pi 0 of it, of course, but then for pi 1, pi 2, and higher homotopy groups, we needed a base point. And if we had morphisms between between two objects in some category which is fibered over some base category, we call it category C, we just said, how do we capture the higher homotopy groups of, let's say f is going from y to x, and I would like to calculate the higher homotopy groups of y. I would say I start from x, which is the base object in my underlying base category. Look at the zero simplex there, pull it back, and then calculate all higher homotopy groups around the base point given by the pullback preimage of that. Here we do not need base points because underlying groups are abelian. homotopy groups is independent of base point. So we do not specify base points here, since underlying simplicial sets are set of underlying simplicial set of simplicial algebra. Simplicial algebra is a simplicial abelian group, and it just turned out that its homotopy group is independent of choice of a base point. So this is what it is. Homotopy is algebra, if you like, of a simplicial commutative ring. It's the homotopy group in each level, and the direct sum of them. So now, what can I say about this graded thing? So the graded abelian group pi lower star of A has a natural structure of a graded commutative algebra. I need to specify why this is the case. It's a graded commutative algebra. So why is that? So let's see. Being a graded group, I think, is obvious. So for any A in, let's say, I take two elements, one in the nth homotopy group of A and B in mth homotopy group of this ring, then I need to tell you how is the product of these two things, right? So we represent in A as a map from Sn, but this by definition really means S1, suspension of S1 n times, right? This is the Sn. We go from S1 to S2 and it keeps us suspended. S1 n-fold suspension of S1, which is Sn, to A. It's true. The space of loops is given as looped maps of loops to the ambient topological space. The space of higher loops is given as maps from higher loops to the topological space. And the higher loops are obtained by n-fold suspension of the lower order loops. So that makes sense. Okay, so and B is a map from Sm to, and this is also like this, to A. So this is the representation of these homotopy groups, where S1 is a simplicial model, for a pointed simplicial circle. This is what we have seen in the algebraic topology 101. Okay, and then we can multiply these elements with each other. So in the group, we can take then, we have two operations. We can take tensor product of A and B, and that's a map from Sn times Sm which sends you to via the two maps to A times A, but of course you have a natural map from here. You can take the quotient by relations and you can go land in there. So that defines for you a map that way. You also have a notion of inner product, if you like, or the dot product of two elements of homotopy groups. And so that is a map from Sn times Sm to A, which like this. And this guy here, this map, is the composition by, this is the multiplication in A. This is the multiplication map. So you take this map and you compose it with the multiplication in A. So then from here you can actually see that. So let's call this thing something. So let's call this thing. Well, maybe you can see that this map, this guy here, satisfies the property that Sn times a point is mapped to 0 in A, and point times Sm is mapped to 0 in A under multiplication in A. So then that tells you that then we see that this map factorizes as Sn wedge Sm as a map Sn as a map AB taking you from Sn wedge Sm to A. And from there you can actually see, since Sn times Sn wedge Sm is just a suspension, so it is homotropic to Sn plus M. So this is the same as Sn plus M. Okay. So as the left-hand side of it is the homotopy type. So this is how you get this graded structure after all. That now you realize that by multiplying objects in this graded pieces of the, computer graded group, you can eventually produce an element in the higher homotopy, a map from Sn plus M to your computer graded. Okay? All right. And so A times B belongs to okay, so this multiplication is associative, unidal, and graded, and graded commutative. Of course, yes. Okay. In the same way, if A in this category and is given, and M belongs to some simplicial A module, this category, if M is some A module, then similarly that you can define homotopy algebra of the simplicial ring A, you can also define for the modules. Okay, so then we get, in the same way we obtain a graded homotopy group of M, which is the sum of the graded pieces pi n of M, and this has natural structure of graded. So can you tell me what does it have? It's a natural structure of what? It should be a module over what algebra? This thing. I star A. That's it. Natural structure of a graded group, graded module. Structure of a graded N. I 0 of A module. I 0 of A module. Has a natural structure. How should I say? Has a natural. Yeah, it's okay. Has a natural I 0 over A graded modular structure. Okay, now for a morphism of simplicial rings, let's say I have two simplicial rings. Again, these are graded pieces, and they have the simplicial relations and so on, and you get this ginormous tower. Really, each time that you look at these things, you should think of a tower like this and all the simplicial relations. If you have the morphism, then you can apply operations. So we obtain two, in fact, adjoint operations. These are the usual ones we have seen before, but this is just a natural extension of it to the simplicial category. So you have one, the operation of tensoring over A with the simplicial ring B, and that takes you from SA modules to simplicial B modules. So that's one. And then you have the adjoint to this thing, which is the pullback via this map F. So if you have modules over here, you will get modules over there by pulling back, and that takes you from simplicial B module category to A module category. But these two operations are adjoint, one of them.
But what is the topological model of a simplicial ring?
Topological model for a simplicial ring. In what sense? What do you mean?
So
What do you mean by this question?
Can I think of A as a topological space with what kind
You
of
definitely you can do it, yes. But you need to make sure that the underlying simplicial set has the structure of rings. It needs to be rings. It should have ring structure.
Is that a topological monoid? Or
Topological, it could be. If you added some monoidal structure, you can define it. I can see that you can definitely define it. But if you want to work with honest topological spaces, you need to really give it an algebra structure. Depends on how you want to define it. It's fine. Underlying set definitely could be simplicial set. You look at the simplicial category of topological spaces. Now you would like to give them the ring structure. You should figure out how.
so the answer is a topological monoid.
Maybe. I haven't done it,
Usually
so I don't know.
Don't think about them underlying topological space.
But you could define it. If you
If
give it some monoidal structure, maybe then that defines
Sure.
for you the ring structure problem.
It doesn't really value much in that kind of, the reason why we introduce the category of simplicial sets is because it's combinatorial and it captures no topological space.
That's true. But it's not impossible to do it. It's not impossible to do it.
I just feel like topological space is easier to understand. This is too abstract.
Yeah, definitely.
Yeah.
But also,
but here's the thing: if you don't have
okay. Yeah, go ahead.
Sorry, if you don't have a simplicial model, how do you keep track of homotopical, like those, like for instance, associativity data, like the fact that those, like those morphisms form an arbitrary topological space? Like I don't know. It doesn't
So
sound.
I think this is strictly.
Think about
Yeah, I know this one is, but I'm saying is if you
can
don't
we
use this
describe rings over
in general
using the check nerves? Can we define rings over category of topological spaces?
Yeah,
so-
well,
You can do it.
If you have any monoidal category, you
Yeah.
have rings and algebras there. But in the case of our,
No, he wants the underlying simplicial set of your simplicial to bring to
Just
be a
take the-
topological space.
just take a
yes,
nerve.
Yeah.
if you're doing this, which we actually will not be doing probably, you can notice that the category of simplicial sets and the category of logical spaces and restrictions in size, they're derived equivalent. So if you identify
No, it might be, but also
Yeah.
still the question is kind of.
I mean, if you take the realization of simplicial set and you go back, you get something which is equivalent and vice versa. Which means that if you take monoids on one side, after homotopy, there are monoids on the other side.
That's true.
And if you have a chosen monoid which is Z, then a map from this Z into your monoid will be an algebra.
It's okay.
But that's definitely not what we want to do, because what we want to do here is.
But my question is, why do you think that finding a topological model for this is easier? I feel like this is easier, actually.
Agreed.
Because this is just a simplicial extension of commutative algebra. It's just commutative algebra with extra relations.
So what do we want to do?
So what actually we want to do is not to take a covariant function, but a contravariant function. You will take the spectrum of this. So you think about these simplicial rings as a diagram of rings. Each ring meaning algebraic functions on a scheme. And then when you go to the category of affine schemes, instead of a simplicial ring, you have a co-simplicial affine scheme. That's exactly what we want. So it is the basic example would be to take any affine scheme and bundle over it, and the sections of this bundle create for you a constitutional affine scheme. This is what we have in information theory.
But this we already have done.
Exactly. Yes.
This already we have done last time.
So if you look at the
Remember how we constructed the schemes over a simplicial category? Algebraic stacks and a scheme over a simplicial category.
oh, there it's simplicial schemes. Here it's
Now he wants to, yeah.
the opposite direction. So
It's
this
the
is
opposite.
what
These are co-simplicial.
the entire kind of thrust of Cohen and Vitsozi is that you need to look not at the schemes, but co-simplicial schemes.
Okay. So, where was I? Okay, so now, moreover, we have the left derived functor over this category, which is the left right tensor product with B, and because we are lifting to the derived, these are, we are lifting to the category of fibrant objects. So now that takes you from objects in the homotopy category of simplicial A modules to the homotopy category of simplicial B modules. The same way that we can have honest tensor product from the category that sends you from category of A modules to B modules, A and B being just commutative rings, and then the derived tensor product takes you from the derived category to the derived category. When you calculate derived tensor product, you need locally free or some kind of injective or projective resolution of objects. Here, an object in here will be fibrant model of what you pick. So this is the analog of that. Or the resolution, simplicial resolution of that object or ring. So note that a non-simplicial, this we discussed last time, but non-simplicial commutative ring will still be regarded as a simplicial object, which is constant in simplicial direction. And so we have this full injection into from category of commutative rings into the category of simplicial commutative rings. So if you have just an honest commutative ring, you just repeat it, and it remains constant in the simplicial direction. Okay. Okay, so you have that. So in fact, this conclusion induces a fully faithful functor from here to here, okay, and which induces a fully faithful embedding of categories from here to the homotopy category of the simplicial commutative rings. Okay? So means that take a ring, put it in here as an object which is constant in the simplicial direction, and then it is realized in the homotopy category by some fibrine model of it, or the simplicial resolution. There is a complex there that realizes that object up to homotopy equivalence. Similar to coherent sheaves. So you also can do it over modules. Take a module, put it in the derived category. Well, a module is realized in the derived category as an object and a complex in some degree, and it has a resolution. So that's the fibrant model for that coherent sheaf or module in that category. Okay. The latter admits a fully faithful adjoint. And what is that? That is the pi 0. It's the one that takes you from homotopy category of simplicial commutative rings back to commutative rings, commutative algebras. Remember that these homotopy groups are the graded commutative algebras, right? So pi 0 in particular. So any object you give me in the simplicial category, I can apply pi 0 to it, and I get back a commutative algebra. Now if
sorry.
Yeah.
The function and its adjoint are both fully faithful?
Yes.
How do I see that pi 0 is actually fully faithful? You're saying that.
How do you see? So I can say it one way myself, via, in some sense, this guy wouldn't have a co-code. So think about an object in the homotopy category. I realize these things. My model always to understand these things is the derived category. So in some sense, it's like taking the zero cohomology of a complex. So does it have any cone? Co-cone? No, right? We don't have anything less than pi 0. Right? So the cone of this thing is just 0. And the co-cone of it naturally is the shifted cone. So
Yeah.
this is. It's like taking the zero cohomology of a complex, which is concentrated always between degree 0 and some higher n. So
Awesome.
it's like that. Okay. But it's a good question. I think this is roughly should be the argument. I just thought of it now, but it's a good question. Okay. I think this should be argument. So now if A is an element of this simplicial commutative ring, is a non-simplicial ring, then we regard it, we regard it as a constant simplicial object. And we get undefined full embedding from category of pi 0 of A modules to the homotopy category of simplicial A modules, and together with the adjoint which is the pi 0 operation, takes us from homotopy category of simplicial modules over A to the pi 0 of A modules. This you can easily see by looking at how I define modules over a simplicial ring. The pi n, so the pi, homotopy algebra of a module over this ring is a module over homotopy algebra of the ring. In particular, in each degree it is the case, and in particular in pi 0 level it is the case. So this is a statement about modules over the ring. Okay. Start from a module of a simplicial ring, and you can calculate its embedding into the simplicial category of simplicial modules, or backwards. That's the pi 0, taking the pi 0 of that module. Okay, so these are the things I wanted to tell you about modules and rings over simplicial in the simplicial category. So now we're trying to move to defining cotangent complex. Okay, so next part is the cotangent complex. So this part is written very formally in the papers of Toen and Vecchi and Metzozi and these people. But let me remind you of Hartshorne because it makes it easier to understand. So remind you something about construction of these sheaf of relative differentials. So reminder from algebraic geometry. So consider that X belongs to category of schemes over some algebraically closed field of characters. So X is a K scheme. Now consider that X in X be the diagonal embedding, the diagonal embedding with ideal I. Okay, so this is the one that sits in the short exact sequence of X sitting inside X cross X. All right, and then consider the ring of holomorphic functions on the square zero thickening of x in x cross x. What does that mean? It means that it is defined by functions which, vanish along not the ideal, because the functions that vanish along the ideal are functions defined on the diagonal. It is the functions that vanish along ideal square. So this is these are given by O of x plus x modulo I squared. And in fact, you can actually see that the spectrum of that thing is the first order neighborhood of x inside the ambient thing. So, and this sheaf sits in a short exact sequence we have all seen in Archer, chapter 2. So this sits as a I squared and O of x cross x mod I squared and O of x cross x mod I. This is correct, right? Okay. So what is this thing? This is the structure sheaf of the diagonal, which is the structure sheaf isomorphic to this structure, pushed over to the structure sheaf of x itself in the diagonal. Well, this is the structure sheaf of the second order neighborhood, or first order neighborhood of x inside x cross x. And this guy is the conormal sheaf, conormal, if you like conormal bundle here. If x is the smooth, it's the conormal bundle of x in the ambient x cross x. Correct? This thing is, in fact, the sheaf of differentials. Conormal is the cotangent sheaf. Okay. So this is what we have seen before. So we get that this guy, omega 1, first order sheaf of differentials of x, sits inside this guy. This is true. Now, the projection x times x onto x. So of course, you can embed x by the diagonal inside here and then project back to a factor of x, and that's identity. So the projection gives a splitting of this short exact sequence. Okay, so if you can, just think about, write this down in the level of holomorphic functions. If you have something like this, it means that you did a map O of x to O of x plus x, and so like that, and you get a map to here, and you can take the quotient to here. So you land eventually on this one. So you get a section onto here, and such that you can prove that this composition is identity on O of x. Okay? So this gives you a splitting in this case, and so we can see that. You can see that O of x cross x modulo I squared will become isomorphic in this case to O of x plus omega 1 of x. Okay. Hence, the data of x and this module, so let's call it some M. Some module over the structure sheaf of X, some M where M is the omega 1 of X is equal to first order neighborhood of X in X cross X. Okay, I hope that you agree with this. And you know, over the simplicial rings, it's exactly the same idea. That's what I'm trying to say. Okay? So now I extend this construction to the category of simplicial rings and simplicial modules on this. So now, go back to the simplicial category, and so let A be a ring here, and M be a simplicial A module. Okay. Consider the simplicial ring A direct sum M. A for you is going to be the module that represents O of X. Okay. Consider this module A plus M, and the multiplicative structure and the multiplicative structure given by, so if I pick some A in here and some M in here times A prime comma M prime, I would like this to be A prime and A M prime plus A prime M. Okay. All right. Now the ring, this is an extension. This gives you an extended ring. This one. The same way that all X cross X modulo I square is an extension of the ring of holomorphic function on X to the first order neighborhood of X inside X times X. This also gives you an extension of this ring, but the extension is defined via this module. If you really think about it, here also the extension is defined via this module. So we are doing the same thing. So this is an abstract way of somehow extending basically your ring by a certain object that behaves very similar to the sheaf of differentials here. Okay, but that object will be for us the module M. So this ring is called, not ring A plus M, with this structure is called extension, the trivial zero extension, because it mimics that idea over there. It's the trivial zero extension. This is a terminology. Trivial zero extension of A by N. Zero extension of A by the simplicial module M over A. Okay? This mimics that idea. So, similarly, we obtain a sequence that A sits inside A plus M, and this surjects onto A. This one takes an element in here to 0, and this one takes an element in here to A. Okay. The set of morphisms over the simplicial commutative rings category, the morphisms A plus M to A is in natural bijection with the set notation is called derivations from A to M. Derivations from A to M. Okay. Derivations from A to M. Derivations from A to M, sending M to the set which is co-represented by an A module in there, which, similar to before, we call it the differentials, which is the A module of Kähler differentials, on A. Now, you might have a little bit of hard time with, in some sense maybe, I mean this is nothing really, it's just a categorical version of the statement that I put before, but at least this part, think about it, this is O and this is sheaf of differentials, and think about the short exact sequence. As soon as we knew that what sits in the middle is O plus omega, goes to O, and the kernel of that morphism is given by omega. As soon as you identify this morphism for me, I can take the kernel and I will get the omega. This is the statement. The set of these morphisms is in bijection with the set of all possible derivations, which are all in the category co-represented by an A module over this category of commutative rings, and that A module is the sheaf of differentials on that. It's exactly like before. The set of morphisms from O to O plus M to O, also there is in bijective correspondence with objects in this category, but these are represented by an actual module over the ring, underlying ring of that category, and that's the sheaf of differentials, Kähler differentials on X. It's the same exact thing. Okay. All right. So, okay. So, by the way, when I say co-represented and so on, the reason to put these extra words in here is remember that these are categorical objects. And we are always working over some underlying category. So we understand all of these things when we look at them fiber-wise over the base category. Right? So this goes back to, we started from category of commutative rings and so on. So we get morphisms to a given ring. Anyway, so this is fiber-wise a statement. You can make sense of this precisely geometrically and identify it with the previous construction as soon as you do it over five minutes over something. Okay. Yeah, just look at the previous notes and you will see what I mean. Okay, so that's that. But then we can go beyond that. We have the sheaf of differentials in commutative algebraic geometry, but we also have the cotangent complex, right? And the cotangent complex has a truncation that gives us the sheaf of differentials, right? So I should be able to define for you some object which behaves very much similar to cotangent complex, and then I need to be able to show you that pi 0 of this object is the cotangent sheaf. the same way that the H0 of the cotangent complex gives me the sheaf of scalar differentials on a variety. So let's do that. Now, we generalize this concept to simplicial commutative rings in the following sense. Generalize this concept, this is already this concept in the following sense. If A is an element in here and M is an element in here via simplicial A module, we would like to lift all of these things to the homotopy category of simplicial commutative. So by applying the above construction, by applying the above construction. By the way, did I make a mistake in the construction of the sheaf of differentials? What did I say? A is what? What did I say? Did I say no? Remove the S, of course. Remove the S and remove the S. We were doing things first over the commutative category, and now we would like to. This is why I got confused. So now we will generalize this concept to simplicial commutative rings. This construction was only over the category of commutative rings. This is why I got confused. I'm sorry. Okay, so now we have simplicial rings, and the idea is that you repeat this construction level-wise. Okay, just level-wise. Construction above, level-wise. For each AN and each MN, the simplicial, the module over AN. Okay, that satisfies the same product structure. For each pair of AN and MN, you can construct the sheaf of differentials, and this way you can get a complex, the simplicial complex. Okay, we obtain now a simplicial ring. If you like, you can just write A plus M, but each time you need to identify whether it's a simplicial thing or not. You can also, sometimes this notation really helps a lot. If you write it like this, distinguishing between this and the one before, so you can write it like that. So maybe I can put dots in here, meaning that these are simplicial objects. So you can construct that ring together with, well, again, a morphism of simplicial this time rings. This is the simplicial extended ring, which is the extension of A by M. Each level satisfies the same properties. Okay. Now, of course, the set of morphisms from here to here is some notion of derivations, but it's a simplicial version of that notion. So, and again, and again, and again, conclude that the set of morphisms in the simplicial, well, this lives inside this category, so simplicial A dot modules in this category is in one-to-one, is an bijective correspondence with R derivations from A dot to M dot. Okay. Of derived derivations from A dot to M dot. Okay. Exactly like before. Okay. Here, okay, so which is defined by homotopy fiber of the natural morphism. Of the natural morphism R hum from A dot and dot to R hum in A dot. Taken as identity. This thing, what this means is, this is the same as the inner hum. You remember we defined the inner hum. This is why we did it. You said that whenever you want to find a notion of homomorphism in a simplicial in the category of simplicial presheaves over a category, then all you need to do in that homotopy category means that you need to replace objects with their fiber models. So you find a simplicial resolution of the objects. So let's say we have some simplicial resolution of A, we replace one of them, and then we calculate this. So this is what we did before. This is the fibrant model for A dot. Same way that if you want to find the morphisms between objects in the draft category, you replace them by their resolutions. Okay. So, taken identity, and that is, we have R derivations from A dot to M is equivalent to R hum. This is my notation R hum over A from A dot to A dot plus A dot. Okay. Here, where hum over A is denotes the simplicial hum sets. Now, as soon as I tell you something, you understand what I'm putting on that flag. A denotes the simplicial hum sets of model category. S commutative over A of commutative simplicial rings whatever over A. Whenever we use this notation, it means that we are looking at the category of objects which all have an arrow, a morphism to a given object. So the way you define this derivation somehow is by the homotopy fiber of this morphism over the identity, which is the same as basically finding this thing over the I dot. I mean, what is this really saying? It's the COCO. That's what it is saying. The derivations are given by COCO. That's it. Look at O of x plus omega goes, well, we did this before. And the kernel of this thing, well, in the category of commutative rings, or sheaf of commutative rings, these are sheaf of commutative rings, commutative groups. This is the cocone of this morphism, right? What am I doing? So I'm applying harm A, and then to this thing. If you apply harm O to this, it goes to harm O to this. And the kernel of that thing, the cocone of this, that morphism, is harm O from here to here. But that's exactly the derivations from O to the sheaf of differentials, because those are given by derivations, right? So this is that very same statement. So just understand this thing. I know you understand. I think this is just an abstract declaration, extension of that one, categorical extension. Okay. It is well known. What time is it? 4:10. It is well known that our derivations from A to something, which is a map from, now it's the derived derivation, so this is from the homotopy category of simplicial A modules to the homotopy category of the simplicial sets. This map is represented by simplicial A module called, do you know what it is called? What is the sheaf harm from O to omega, which is the cocone of the sheaf harm from here to here, morphism from omega plus O plus omega to O comma O. The kernel of that thing is the cocone in its own category is the sheaf harm from O to omega, but that is omega, right? That is just the sheaf harm itself. So this one is the A module called L dot of A. Called the cotangent complex of this simplicial ring A dot. Okay. And certainly, actually, we have already defined a notion of algebraic schemes over commutative rings, or the category of commutative rings. Certainly, you can just lift that construction of the schemes and the stacks and so on that we discussed to the category of simplicial commutative rings. And then you can define an affine scheme, and you embed it diagonally inside the product of itself. And this really is the cotangent complex that you get from the previous discussion. But this is the simplicial affine scheme version of this construction that I just mentioned. Okay, so this is called the cotangent complex to construct L dot of A. How do we construct it? We know how to construct sheaf of differentials. So to construct it, let Q of A dot to A dot be the cofibrillant model for A dot. Now apply the construction of Kähler differentials, for Q of A dot level-wise to obtain, to get a simplicial Q of A dot module omega 1 of Q of A dot, then set or define L dot over this simplicial ring A dot. By the way, this is also every A that I'm putting here has a dot in it. L dot of A dot is omega 1 of the cofibrant model shift of differentials over this resolution of A dot, drag tensor product with over Q of A dot with A dot. This is what it is. This is something that lives inside the homotopy category of simplicial A modules. Compare this with the cotangent complex. When you want to construct the cotangent complex of a scheme, if you remember from algebraic geometry, you knew that you cannot intrinsically just define it. You need to embed your scheme in the ambient to smooth the scheme. And then you start constructing. What you do is you embed your scheme singular, it could be singular. If it is not singular, it's cotangent complex, just collapses to one term only. So it's in this categorical version, it will be just homotopy equivalent to its pi of 0, which is just a shift of differentials. But if it is singular, you need to somehow realize the cotangent complex as some sort of resolution of pullback of a cotangent sheaf of something is smooth to the singular scheme. So what do you do to construct a cotangent complex? Ilusi or Grothendieck or whoever, they tell you what to do. You embed your scheme in ambient, a smooth guy. The smooth guy has a sheaf of differentials. You pull it back, the zero term of your cotangent complex literally will be restriction of some cotangent bundle of some ambient space to your scheme. But is it perfect? Is it remaining as a bundle? No, it has higher cohomologies. This restriction, because this restriction is a derived tensor product. So then you find the resolution, and that's the cotangent complex. It's the same thing in here. So what I'm saying is, if you construct some scheme out of this thing, this is very compatible. You take the pi 0 of this one, you will just get omega 1 of the pi 0 of A dot. Similar to before that, in the regular algebraic geometry, H0 of the cotangent complex is the sum sheaf of differentials in the end. Okay? From the resolution of the structure sheaf of S in the ambient, the smooth variety. Okay, so this is kind of very much rhymes with what we know. So now, with this construction, we can realize in this map A dot to cotangent complex of A dot as the derived contour for that. Okay. Moreover, by adjunction, we have an adjunction that we had, remember we had two morphisms, one fully faithful embedding of category of commutative rings into the simplicial commutative rings, as well as the fully faithful induced embedding into homotopy category of simplicial commutative rings. We had an adjunction for that composite morphism, which was taking pi 0, which he asked why is it fully faithful. So here, if I apply that adjunction, I can take an adjunction from homotopy category of simplicial commutative rings to commutative rings, and see that if I took pi 0 of this object in this homotopy category, I would have just gotten the sheaf of differentials over pi 0 of my simplicial commutative ring. Okay. Oh. Remark. This, yeah, so this is maybe good. So the cotangent complex, L dot of A dot is factorial in A dot. So it respects morphism of simplicial commutative rings. And of course, it's also factorial in the regular commutative category, as we have seen before. If I have morphism of rings and I have the schemes defined on them, each one have the cotangent complexes, and also you can take the morphisms between them. So hence, for any morphism of simplicial commutative rings, let's call this A to B, dot B dot, we obtain a morphism L dot of A dot to L dot of B dot, okay, in homotopy category of simplicial A modules, A dot modules, because this is an A dot module, okay, and this one is, and this one is too, because this one is a simplicial B dot module, which itself is an A dot module. So, and by adjunction, this morphism can be considered as a morphism in fact, homotopy category of simplicial B dot modules, L dot of A, derived tensor product over A dot with B dot, taking you to that now, right? So, yeah, so you can now realize it as a morphism of objects in the category of B dot modules. You can realize it as a morphism in the category of A dot modules, or if you pull this back to B, this is the pullback. Now everything is morphism in the category of B dot modules, right? Well, I believe these things we have seen before in the usual non-simplicial category. So the homotopy, final remark, the homotopy co-fiber of this morphism is denoted by L dot of B dot over A dot, cone, basically. The cone of this morphism is, so you have A morphism of rings that defines, let's say, if you naively think about these as commutative rings, the spec of A, B goes to the spec of A, right? This we have seen before. Call this the scheme over B, the scheme over A. This one has a cotangent complex. This one has a cotangent complex. If I pull this back, I get the pullback, but this is more morphism. I get the pullback of cotangent complex of A, but that is the same as cotangent complex of A, derived tensor product with the structure sheaf of B. And this is the five-rank model for the structure sheaf of B if B is a simplicial commutative ring. Okay, so I get the map from pullback to L dot and B, and the cone of this thing, which is the homotopy cofiber of that morphism, is the relative cotangent complex. So this is denoted by the L dot of B dot over A dot, and it's called relative cotangent complex of B dot over A dot. So everything really rhymes with what we had before. I think this is actually a good place to stop. Any questions?
Awesome. The reason to introduce simplicial ring is to find a good resolution.
Yes, that's right. That's right.
So
Later,
So in the category of scheme, we don't have such.
no, not really. Yeah. So the reason we are doing this thing, I tell you this. Look, think about object in the derived category, how nice these objects are. Object in the derived category is not only a geometric object, but it also contains cohomology classes. The difference between cotangent bundle of some variety and the cotangent complex of some variety is that, in some sense, I mean, if the variety is nice, these two notions coincide. But if the variety is not nice, like singular, you construct some geometric object that also has some cohomological data, and the cohomological data gives you a measurement of how unnice this object, this space is. We are trying to do the same thing. We are constructing geometric objects which also have the structure of higher homomorphisms. And infinitesimally, these are higher cohomologies. So for instance, later, we know, of course, by Fulton or by SGA7, by Grothendieck himself, that when you do intersection theory, if you have two spaces which are intersecting not nicely, you need to use some kind of cohomological technique to intersect them. You use cotangent complex. This is what we are doing in here. We don't want to just associate some cohomology class to some kind of bizarre intersection of two space. We would like to associate with an object which is still geometric, but is equipped with this cohomological or higher homotopical data. But this is why we're doing this. And very similar to, someone asked you, why do we need cotangent complex rather than cotangent sheaf? Cotangent sheaf is nice. Well, tell me what you can do with cotangent sheaf when two spaces, coincide in a non-transverse way. You cannot work it, but with cotangent complex you can. Similar to here. Okay? Now, the discrepancy between this homotopy theoretic construction and what we already use, I mean, we already in algebraic geometry have some object which has all of these properties. So far, I haven't told you why derived algebraic geometry is better than algebraic geometry. Because we already have this object. We can, in fact, restrict this to the category of commutative rings over some characteristic zero algebraically closed field, and we just recover everything that we had before. That you will see later. There are certain examples in moduli theories that you just realize with this construction you can do things that with the even cotangent, working with the objects in the derived category of the scheme you cannot. That you will see later. But so far, this is just a categorification of what we have seen in the language of Illuzi and Grothendieck. Okay? That thing is also categorical. I cannot say it's not categorical, but this is a bit more categorical flavor than that, because it's over general categories. Any other questions? Okay, so let's see you guys next time. Dennis will be the
Because I thought that you are.
Yeah, I'll want to
Oh.
talk about. Yeah.
Yeah,
Yeah.
who's gonna do
I
it?
mean, I can do it. Yeah, I can do it. Just
Yeah, so if we
Probably-
do it, yeah, so you want to do it next time so that
yeah, I can do
as an
it.
example of bungee
The
and
thing
all the
is,
structures.
I will use some things that we have introduced. Like I might have to, the audience might have to take faith when I say certain things. Or would you want?
Very faithful people.
I mean, or would you prefer to keep it later? Because like once we, like I need to do things like I don't know, like I need to do things with like saying certain pre-stacks and different theory, and then do
Actually, it will be very good before we continue, maybe because
It's good, yeah.
it will give us an example of why what we will be
take a look at like how you use it.
Yeah, maybe you can throw a heavy ball in the middle of the course and then tell people this is what it is and we need to work with it. So later when Dennis continues,
Yeah, sure.
we can see that we are going there. That's